Hi, I'm Carl, one of the applications engineers here at Teledyne LeCroy, and I would like to answer the frequently asked question, how do I set up serial data analysis software to quickly make jitter measurements? Using the SDAIII complete link option on a Teledyne LeCroy digital oscilloscope allows us to make jitter measurements with jitter breakdown quickly and accurately. Let me show you how. Today we are using a WaveMaster ATI oscilloscope, but this answer applies to all of our Maui Extreme oscilloscopes that have the serial data analysis option. We're viewing a 2.5 gigatransfer per second PCIe data stream generated by the PERT Phoenix protocol-aware bit error rate tester. To start, we select Analysis and Serial Data. Beneath the SDA tab, we check Enable SDA and check Lane 1. SDAIII Complete Link has multi-lane analysis capability, so you can view, in real time, the effects multiple streams of serial data have on one another. We will be setting up one lane of data for analysis, but the steps may be repeated for each lane in use. We then select the Signal tab. We set up the serial data inputs by choosing one or two inputs. We are viewing a differential signal where the positive side is connected to channel 1 and the negative side is connected to channel 2. So we will select input 1 minus input 2. If we were using two single-ended probes, we would select input 1 minus input 2 as well. If we were using a differential probe, we would select one input. Beneath signal type, we set PCIe 2.0 2.5 gigatransfers per second. We then select the clock tab and select Find Right Now. We check PLL on beneath PLL setup to enable the phase-locked loop to extract a more accurate clock from our serial data stream. If we were using spread spectrum clocking, we would change the PLL type to be a two-pole filter. However, with SSC disabled, the default setting is adequate. Now we select the Jitter tab. Check the Enable Jitter Measure box. The Pattern Analysis button should show a green indicator and report Pattern Found. SDAIII jitter calculation methods require a repeating pattern. TJ, total jitter, RJ, random jitter, and DJ, deterministic jitter parameters are now displayed. We see options here to set a jitter filter or view jitter characteristics with jitter track, jitter spectrogram, jitter histogram, and jitter parameters. We select jitter track and enable Show RJ BUJ track, which is a display of random jitter and bounded uncorrelated jitter values in the same time domain as our source waveforms. We select jitter spectrum and enable RJ BUJ spectrum and show PJ inverted FFT for jitter spectrum analysis. We select jitter histogram and enable RJ plus BUJ histogram, which shows us the distribution of jitter values. Lastly, we select jitter parameters and enable parameters in addition to the TJ, RJ, and DJ jitter breakdown that is already displayed. We can see we have around 200 picoseconds of periodic jitter. In the RJ BUJ histogram, we see a bowl-shaped jitter distribution. We can see that the source of jitter is not random, which would be a Gaussian distribution. Rather, this bowl shape is typically seen with periodic jitter. Looking at the jitter spectrogram, we can see we have one large peak, indicating a majority of the jitter is at a single frequency. Using the PJ inverse FFT plot, we can set up a frequency measurement to find the frequency of the jitter. We can see the frequency from the PJ inverse FFT plot is around 10 MHz. We can also change the source of that frequency measurement to the jitter track and see that we are still seeing around 10 MHz. We can zoom in on the track and we can see this is a sinusoidal distribution of jitter, otherwise known as periodic jitter. Periodic jitter could be caused by an aggressor signal coupling into our serial data. In this case, I would suspect some sort of periodic signal like a 10 MHz clock. Since our signal source is the PERT Phoenix protocol-aware bit error rate tester with controllable jitter sources, troubleshooting the problem will be much easier than what most designers with jitter problems would face. We minimize the Extreme Oscilloscope application, and in the PERT Phoenix software we can see we are generating 200 picoseconds of sinusoidal jitter. In SDA Complete Link, we can see that we have excellent correlation between our jitter source and result. We disable the high-frequency jitter source. We go back to the Extreme Oscilloscope application, reacquire our data, and we can see we have a Gaussian distribution of random jitter. That was an easy fix. This is how we set up serial data analysis to quickly make jitter measurements. For more answers to frequently asked questions, go to teledynelacroy.com/FAQ.